Hey there. Today we have a few things I'd like you to do. The first thing I'm going to do is I'm going to go through just some review of terminology. You may have seen some of this before. Some of it might be new, especially a review of factoring, quadratics, and even cubics. And then I'm going to have some problems for you to try and a couple of worksheets for you to work on. So we're going to start off by talking about number set review. On your test, there was one question, the pretest, it had the square root of 0, and it just said, what number sets does this belong to? Excuse me. And a lot of you just didn't know what that meant, so I just wanted to talk through number sets. So one number set that's really important to know is called the natural numbers. Usually we call this a bold N. It's the natural numbers. And the natural numbers are often called the counting numbers as well. So the natural numbers is a set of numbers 1, 2, 3, 4, etc., all the way off to infinity. So the counting numbers, because it's how you count, right? There's one thing, two things, three things, four things. No decimals, no fractions, no negative numbers. Just the plain old counting numbers. So the way sometimes you'll write that something is in the natural numbers, right? So all these members, 1, 2, 3, 4, these are members of the set or elements of the set. So we can write things like 3 is an element of the natural numbers. So this is 3 is an element of the natural numbers. Okay. Oftentimes in proofs, you only want to deal with natural numbers or something like that. So it's important to be able to say, x is an element of the natural numbers. So you're saying any x can be any natural number you want. Next set that's really important to know is the integers. So bold Z. And the integers has all the positives and negatives, but still no decimals, no fractions, right? So you have the negatives, so everything from negative infinity, -3, -2, -1, 0, 1, 2, 3, all the way off to infinity again, right? So -5 is an integer. 7 is an integer. Sometimes you also see things like this, like pi is not an element of the integers, right? Because pi is like somewhere between 3 and 4. Pi is, however, a real number. So a real number is anything you can put on a number line, right? So, for example, the square root of 3 is a real number, but it's not an integer, and it's definitely not a natural number. Pi is a real number. E, if you know E is 2.71 and change. It's called Euler's constant or Euler's number. It's really important, especially in finance. Also, lots of kind of real world examples, but it's kind of cool. But real numbers, anything positive, anything negative, right? But it can be like, I don't know, 7.68 is a real number. Another one you see a lot is called the rationals. We use Q for the rational numbers. Rationals. I realize I didn't write integers anywhere. Z is the integers. It's Z because the German word, I believe for numbers or counting, someone can tell me, I think it's Zahlen with a Z. That's where the Z comes from for integers. Q comes from quotient, right? Quotient. So it's rationals. Rationals are anything that you can write. Sometimes this is called set Buller notation. They write it this way: A over B, where A and B are integers. But B, of course, cannot be 0 because you're not allowed to divide by 0. So some examples: 3/4 is a rational number. -7/15 is a rational number. 22/8 is a rational number, right? As long as you have a integer on the top and bottom, those are all going to be rationals. These are the ones that come up the most. Sometimes you'll see things like this. This means only positive real numbers. Positive reals. You see that sometimes with the integers as well. Only positive integers. That's exactly the same thing as the natural numbers, though, right? Positive integers, 1, 2, 3, 4, 5. It's exactly the same as the natural numbers. Yeah, it's kind of what you need to know about number sets. So good to know. Naturals, integers, reals, and rationals. Those are numbers sets that you'll see often. All right, let's talk about factoring. So first of all, what do I mean when we talk about factoring? Well, factoring means we're taking some kind of a quadratic, usually. It could be a cubic or a quartic. It could be a higher degree polynomial. But what you're trying to do is you're trying to change it into some kind of set of factors, right? So if it's a quadratic, there are going to be two factors because you'd have an x here and an x here. And there's something, sometimes you see like a plus p and an x plus q, right? And p and q could be in the integers. You might have something in the front of this too, like there might be a, I don't want to, you know what letters to use here. Let's say there's like an L here and an M here, right? And L, M, P, and Q, you want all of those to be integers, right? So whenever we're factoring, right, these are factors, right? And factoring, kind of the most basic idea of factoring comes from factoring numbers, right? Like for example, the number 24. One way to factor 24 is 3 times 8. Those are factors that multiply to make 24. Factoring a number like, I don't know, 72, right? 72 is 9 times 8. It's not the only way to factor 72. In higher level math classes, you talk a lot about unique factors. And this you could prime factor, right? 3 times 3 times 2 times 2 times 2. It's called a prime factorization of 72. Every integer has a unique, or I should say natural number, has a unique prime factorization, which is kind of cool. But problems that you've hopefully seen before, and if you haven't seen factoring before, please come talk to me. I've got lots of practice I can give you and good videos you can watch. But today I'm just going to kind of do some examples to remind you how to factor. I always do factor by trial and error. So for example, let's say we have x squared plus 12x plus 35. Now some of you may have seen models with an x where you write like 1 at the top and 35 at the bottom, and then 7x and 5x, things like this. I do not recommend those, and I'll tell you why. For one, it's slow. It takes a long time. Also, it does not make you a better mathematician. Being able to do this with trial and error really makes you better at multiplying, it makes you better at foiling, it makes you better at expanding. These are really good skills to have. So when I see this, I'm like, well, it's got to be x and x, right? Because x times x is the first terms that's going to give you x squared. Then I look at the last term and I see 35. I think, well, there's not a lot of ways, right? When you foil, and if you don't know what foil is, what I'm talking about when I say that, let's say we have like x plus 6 times x minus, I don't know, 3. This is, you foil to expand this, right? The first terms, so F-O-I-L, the first terms make x squared. I promise I'll come back to the factoring problem. The outside terms, that's the O, the outside terms make a negative 3x, the inside terms make a 6x, and the last terms, F-O-I-L, first, outside, inside, last, the last terms make a negative 18. So altogether, we have x squared plus 3x minus 18. And factoring is trying to go backwards, right? So when I look at the problem from before, I'm going to delete all this because we don't need any of that. Go away. Goodbye. All right. So going backwards here, what I'm doing is I'm saying if I foil this, whoops, better if that was a pen. If I foil this, it's got to get me back to here. So x times x, those are the first terms, are going to make x squared. And then I'm ignoring the inside-outside terms. I'm looking at the last terms. The last terms have to make 35. So if the last terms have to make 35, like I said, I don't have a lot of choices. 7 times 5, probably, right? It could be 35 and 1. It's never 35 and 1. If you've ever factored before, it's like never 35 and 1. It could be, but then this number sometimes gets pretty big. So I'm going to put a 7 and a 5 here. And the reason I know it's 7 and 5 is because 7 plus 5 makes 12. So now the inside terms and the outside terms also make that 12x. So when I factor, you'll hear me say a lot of things like, can I make 12, right? And that 7 and that 5, when I add them together, they do make 12. So now I know it's all going to be plus because you're just foiling in your head. X times x, x squared, perfect. X times 5, 5x. X times 7, 7x. 5x and 7x makes the 12x, and then 7 times 5, 35. That is the factoring for x squared plus 12x plus 35. Next one, if you want to try it yourself, you can. X squared minus 3x minus 28. It's a little harder, but if you want to pause the video and try it, you can. I'm just going to set up my factors. X squared, x and x. Boom, done. 28. Got some choices here for 28. It could be 2 and 14. It could be 7 and 4. It could be 28 and 1. I think that's all that can be. So what I'm doing is I'm looking at these. I'm trying to see which one can I make a 3 out of, right? I'm trying to make this 3x in the middle here. So they're going to multiply to 28, but they need to somehow add or subtract to make a 3. Well, 2 and 14 could make a 12 or a 16. That's no good. So it's not that one. 7 and 4 could make an 11 or a 3, right? If I subtract 7 and 4, they somehow make a 3. And don't worry about the negative for now. We'll figure that out later. 28 and 1, when I add them or subtract them, I could make a 29 or a 27. No good, right? So it's going to be 7 and 4 for sure. And now last, I always do the positive and negative signs. So here, I want a negative 3x when I'm done with my inside and outside terms. That means I need a negative 7 and a positive 4 because that'll make a negative 7x and a plus 4x, and that'll give me my negative 3x. You can double check it if you want to. You can FOIL it, go backwards, and see if it works out, but it does. It should be just fine. All right. There we go. So we have our factoring for the first two. I got one more where a is 1, and then you guys, I'll get some harder ones as well. So here we have x squared minus 13x plus 36. If you want to give this a try, feel free. You can pause the video, but I'm just going to keep going here. So 36, got a few choices, 6 and 6. 6 and 6, if I add and subtract those, I could make 0 or I could make 12. I want 13 though, so that's no good. Let's see, it could be, what, 2 and 18? 2 and 18 could make a 20 or it could make a 16. I want 13 though, I'm not quite there, I'm missing something. Let's see, it could be 3 and 12. 3 and 12 could make a 15 or a 9, but that's no good. And I'm kind of dancing around it because I want you to see what happens in my head. It's 9 and 4, right? 9 and 4, I could make a 5 or I could make a 13. Here we go. So x and x, 9 and 13, 9 and 4, excuse me. Now this time I need a negative 13, negative 13x. So they're both going to be negative. That'll give me a negative 9x and a negative 4x and a positive 36 at the end, which is exactly what we want. All right, so all of these had something in common. The a here in front of the x squared, there wasn't one, right? Which means it's 1. When a is 1, factoring is pretty easy. When a is not 1, when a is not equal to 1, things get quite a bit more complicated. I'm just going to add another page here. See if I can do it here, because we're going to need it, I'm pretty sure. All right. So if a is not equal to 1, things get a little bit more tricky. So let's take a look. Let's try 20x squared plus 19x plus 3. So this is still not too hard, but it's not easy. The reason this is harder is because now I need to make a 20x squared. All of the ones before, it was just x squared, and that's just x and x every time, right? Now the 20, I have some choices. 20x squared could be 1 and 20, 1x and 20x. It could be 2x and 10x. It could be 4x and 5x. I think that's it. Those are all my options. Now I'm going to make a recommendation to you. I always start in the middle, because the bigger the numbers you have, the bigger the numbers get later on over here, and generally they're not that huge, right? We have a 20 or 19 and a 3. They're not giant numbers, so I don't think it's going to be a 20 and a 1. I'm going to try 4x and 5x, and we'll see what happens. Now 3 is a gift here. The only way I can make a 3 is 3 and 1. But the reason it's harder when a is not 1 is because it could be 1 and 3 or 3 and 1, and before it didn't matter, right? Like up here, when I had the 9 and 4 here, right? It doesn't matter which order I do this. I could put the 4 here and the 9 here, and it's still going to work the same way because there's nothing in front of the x's here. I'm going to get 9x this way or 9x this way. It doesn't really matter where it is. Here, though, if I put the 1 here, that's going to give me 5x. And this 3 here is going to give me 12x when it multiplies by the 4. Down below here, the 3 is going to give me 15, and the 1 is going to give me 4. So with the 1 and the 3 here, sometimes I usually do all of this in my head, but I'm going to write it down over here for this one. So here I would get 5x and I would get 12x. 5x and 12x, I could make a 17x, or I could make, a 7x. I don't want that though. I want 19x when I do the inside and outside terms. The other one gives me a 15x. That's 3 times 5 here. And the 1 times 4 gives me a 4x. Ah, here we have a winner. That'll make 19x, right? I'm just foiling in my head all the time. 4x times 5x gives me 20x squared. Now when I put a 3 here and I put a 1 here, so I'm using this guy down here, that's going to give me a 15x, and it's going to give me a 4x, which gives me 19 total. So it looks like everybody's happy here being positive, right? Because we get a positive 3 and a positive 19 when we FOIL it out. You can FOIL it out again, check my work, see if it works out, but that should be our factoring for 20x squared plus 19x plus 3. All right, another one. You can try it on your own if you want to. Got a little messy there, so let's divide. So we have 12x squared minus 7x minus 12. And we're trying to factor this. So I'd recommend starting like we did here by thinking, how can I make 12x squared? And you've got a few options. I'm going to go ahead and work on this now. So like I said, I like to start in the middle. I'm going to try 4x and 3x. It could be 6 and 2. It could be 12 and 1. I like to start in the middle because often that's the answer, if I'm being honest, right? But it could be wrong. We'll see. So 4x and 3x. Now 12 over here, once again, I've got some choices. Could be 12 and 1, could be 2 and 6, could be 3 and 4. I'm again going to start in the middle. So let's see here. It could be 4 like this and 3 here, or it could be 3 here and 4 here. If it's the top one, right, if it's this guy here, 4 times 3 is going to give me a 12x. 3 times 4 is going to give me another 12x. 12x and 12x could give me 0, or it could give me 24x. Neither of those is what I want. I want 7. Let's try the other one. 3 times 3 is going to give me a 9x, and 4 times 4 over there is going to give me a 16x. That could make a 25x, or it could make a 7x, right, if I subtract. So I'm going to put in the 4 and the 3, using the bottom one, because that's the one that worked out. Now I need to make my signs work out. I need a negative 7x. Negative 7x. So I want the 16x to be negative. So when I multiply this 4 by this 4, it needs to be negative. So I'm putting a negative in front of the 4. And then I'm going to need a positive 9. So I'm going down to negative 16, back up 9, which gives me the negative 7. And there is our factoring. 4, 12x squared minus 7x minus 12. I got one more. It's not too bad. We got 6x squared. Divide it out again here. 6x squared minus 31x plus 35. Think about the factoring for that guy. Let's see. 6, probably going to be 3x and 2x. Right? It could be 6x and x, but I'm going to try 3x and 2x first. I'm going to put it here. If it's wrong, I'll erase it later. 35, almost certainly 7 and 5, right? It could be 35 and 1, but 35, if I put a 35, look at this, in either one of these places, I'm either going to get 35 times 2, which is 70, or 35 times 3, which is 105. No way either of those is going to get me to 31, which is that middle term. So probably going to be 7 and 5, so it could be 7 here and 5 here. It could be 5 here and 7 here. If I do the first one, 7 times 2, let's do that, 14x. 5 times 3 is going to give me a 15x. That could add to 29x, which is close to 31, but no good. Not going to work. The second one, let's see, 7 times 3 gives me a 21x. 5 times 2 gives me a 10x. If I add those together, that'll give me 31x. That's a winner. That's what we want. So I'm going to put my 5 here, my 7 here. Now I have to figure out our signs. Let's see. Well, I need both of them to be negative, because I need negative 21 and negative 10 is going to give me that negative 31. So when we do practice, like little games in class that seem fun when we're doing multiplication and addition and subtraction of integers, it's really important that you can do those things quickly because it makes things like factoring way easy. All right, last thing I'm going to do here for factoring is talk about sum and difference of cubes. Sum and difference of cubes. What does that mean? That means if you have something like x cubed minus 8, right? Something like that. This is a difference of cubes because it's x cubed minus 2 cubed, right? This is a difference of cubes. And when you have a difference of cubes, you always factor it the same way. And what I want you to remember is the acronym SOAP. Let's use a different color here. I'm not using a different color yet. S-O-A-P. SOAP is how you factor a sum or a difference of cubes, and I'll show you what that means. So what I'm going to do here, so I have x cubed and 2 cubed. So the first thing I'm going to do is I'm going to write down x minus 2. You can get into some deep reasons why this works. It has to do with synthetic division and finding zeros of polynomials, but that's stuff that we haven't done yet probably, so we'll do it later in the year. But what the S stands for is same. Same. The O stands for opposite. And the AP stands for always positive. So the first sign, notice, is the same as the sign over here, right? Negative here, same sign here. Where did the 2 come from? It's the cube root of 8, right? Cube root of 8. So 2 cubed is what made that 8. So we have x minus 2. Now we're going to have the opposite sign. So I'm going to have an x squared. Opposite sign of the negative over here is a positive. And then I'm going to multiply the 2 and the x. We're going to have 2x. And the last sign is always positive, and it's going to be 2 squared, which is 4. So this formula always works. So whatever the cube root of this guy is what goes here. The first thing squared goes here. the multiplication of the two things goes here, and the last thing is the last thing squared. And you can check this, right? We can check our work. Let's see if it works. So if I FOIL this out, well, not FOIL, but expand, we're going to have x cubed, that's x times x squared, plus 2x squared, and then plus 4x. So that was multiplying x by each of the three terms. And then we're going to have a minus 2x squared. That's looking good. Those cancel. Then we're going to have a minus 4x. That's good. Those cancel. And then we're going to have a minus 8, which is exactly what we started with, x cubed minus 8. So in general, if you ever have any kind of x cubed minus y cubed, x minus y, same sign, right? Same first. Then the opposite, so we'll have x squared plus xy. And then the last sign is always positive, plus y squared. This is the formula for factoring a difference of cubes. Sum of cubes is the same thing. If I have x cubed plus 8, that is x cubed plus 2 cubed. And the way that that factors, we're going to do the same sign, so x plus 2. Then the opposite sign, so we're going to have an x squared minus 2x. And then the last sign is always positive, so we'll have a plus that last thing squared, right? The y squared at the end, so that'll be a plus 4. Factoring sum and difference of cubes, when you first do it, it looks kind of weird. It seems like a trick that shouldn't work. You have to use synthetic division to prove it, so I'm not going to do a proof of why this works. But if you remember SOAP, and you remember that like inside you have the smallest things, right? You start with the smallest things, so the cube root of both, and then you have a square, and then a multiplication of the two, and then the square at the end. All right. Moving right along. Let's try one that's a little bit more involved here. The formula for x cubed plus y cubed, right? So this is true for any cubes that you have, minus. X cubed, this is plus, I was right, sorry. So we have x plus y, same sign, right? Plus, plus. Now we have the opposite sign, so x squared minus xy. And the last side's always positive, so plus y squared. SOAP, S-O-A-P. Same, opposite, always positive. So same sign here, opposite sign here, always positive at the end. So those are our two formulas for sum and difference of cubes. So now, a couple that are, well, just one. I got one that's a little bit harder, so let's do an example here. Let's say we have 64x cubed minus 27y to the 6th. So when I have something like this, I like to think, what is actually being cubed? Well, the cube root of 64 is 4. So this is 4x, that's all cubed, minus 27y to the 6th, that's 3y squared cubed, right? Because when you have power to a power, that's an index rule. You multiply those powers together. So if I'm going to factor this, right, using our formula up here for difference of cubes, I'm going to do SOAP. So same sign, so it's going to be 4x minus 3y squared. Now it's going to be the opposite sign, so I have to square the first thing. So it's going to be 16x squared. Opposite sign is a plus. Now I multiply the two things together, so it's going to be a 12xy squared, right? From our formula, you just multiply the two things together. And then always positive, so the last thing is going to be positive at the end, and that's going to be the last thing squared. So that's going to be a 9y to the 4th. And you can expand that out and see if it works, but it should. That SOAP formula always going to help you if you have sum or difference of cubes that need to be factored. You might be asking, why is the factoring important today? You're going to get to some rational expressions that require factoring to cancel things out and simplify. Get to that in a moment. So, speaking of canceling things out and simplifying, a few more terms you need to know. LCD stands for least or lowest common denominator. So least or lowest. That's a terrible W. Let's see if we can do better. Least or lowest common denominator. So for example, if you're trying to add two fractions together, let's say you have, let's start easy. Let's say you have 3/2 plus 7/4, right? I want to have the common denominator. The denominator has to be the same to add fractions. So what I do over here is just multiply by 2 on the top and bottom to make it 6/4 plus 7/4, which is of course 13/4. So notice I didn't have to multiply them together. There's some people that always multiply the two together. You don't have to do that, right? As long as they're the same, find the lowest or least common denominator to make your life easier. So for example, if I had x over, let's say 8 minus x plus 7 over 6. So some people would look at this and say, oh, 48, you have to multiply 6 and 8. 48 is your common denominator. But it's not the least common denominator. I could do better. I can get both of those to be 24. Multiply here by 3 over 3, here by 4 over 4. We're going to have 3x over 24 minus 4x plus 28 over 24. Tricky thing here, that negative sign is going to distribute to both of these. You're going to see problems just like this on the worksheet I'm about to show you, so that's why we're going through this. So we're going to have 3x minus 4x minus 28 because of that distribution. They're implied brackets on the top of a fraction always. On the bottom, 24. That is a negative x minus 28 over 24. We have now combined and fully simplified that subtraction of fractions. Common fraction. Common fraction is an integer over an integer. A over b, where a and b are both in the integers, right? So, for example, 3.6 over 7 is not a common fraction because it has a decimal on the top, right? 4/19 is a common fraction. I don't know, 7/5 is a common fraction. Negative 18/23 is a common fraction. It doesn't have to be simplified. Let's say like 3/9. 3/9 is 1/3, but it's a common fraction. A complex fraction is more complicated, obviously. It has a fraction on the top or bottom of the fraction bar. So like 1/3 plus 1/2 over 2/3, something like this. That's a complex fraction. And to simplify that, remember there are implied brackets here, so we're going to do that first. So 1/3 plus 1/2, that's 3/6 plus 2/6. Nope, that's a lie. That'd be 1/2. 2/6 plus 3/6. There we go. Divided by 2/3. That is 5/6 divided by 2/3. And of course, when you divide by a fraction, you multiply by its reciprocal. So this is 5/6 times 3/2. Multiplying fractions, you just multiply straight across. So we have 15 over 12, which you could reduce by dividing by 3 is 5 over 4. You could have done that here too. If you see this 3 over 6, realize that's 1/2. Right away you could say, oh, this is just 5/4. Right? However you get there though. And that actually did the job of simplifying. To simplify a fraction, there must be no common factors on the top and bottom. So for numbers, that's pretty easy, right? If you have like, I don't know, let's say 8/22, right? This is not simplified because you can divide the top and bottom by 2. 4 over 11, right? That is now simplified. It's harder though if you have something like x plus 2 times x minus 7 over x plus 2 times x, I don't know, plus 1, right? When it's written in factored form like this, it's really easy to see, oh yeah, I just cancel out the x plus 2's. But the way that they're going to give this to you is not like that, right? They're going to give you x squared. Let's see, plus 2 minus 7 minus 5x. That's not a 5. Minus 14. And then on the bottom, they're going to give you x squared plus 3x plus 2. They're going to give you this problem, and they're going to say simplify. And now you might be saying, now I see why I need to know how to factor. Because you need to be able to transform this to that, and this to that, and then you see the x plus 2's cancel. X plus 2's cancel, your final answer is x minus 7 over x plus 1. But there's one sneaky thing, right? We talked about this before a couple times. The bottom cannot be 0. So denominator cannot be 0, ever. And that's true in any part of a problem like this, right? So from the very beginning of this problem, I have two problems. X can't be negative 2, and x can't be negative 1, because those two numbers would make these factors on the bottom 0, and that's no good. So the way that they usually write that is like this. X cannot be equal to, and they put these little curly braces here, negative 2 or negative 1. And what that means is this is a set of numbers, right? It uses the curly braces. I usually make the curly braces really fast and they look really bad. That one actually wasn't terrible, but you'll see this in some of the solutions to the problems. I just want to make sure you knew that's what it means. So x is not allowed to be either of these two numbers, even though there's no x plus 2 at the end here. It's like a ghost. It's like it's still hiding there. From the beginning of the problem, that's when you should be looking at your domain restrictions. So factor. So basically when you're given a rational expression, this is what we're focusing on for this first unit. That's a terrible A though, let's make it better. So if you're given a rational expression, and all a rational expression is something on the top, usually some kind of a polynomial, and something on the bottom, right? Rational is ratio, right? It means you have some kind of a fraction. So up here, this is a rational expression. Something on the top, something on the bottom. And usually what you're going to do is you're going to factor. You're going to note domain restrictions. So you're going to use that set notation to do that. And then you're going to cancel factors, cancel common factors. And that's your simplified form. I believe that's it. So all of these notes, hopefully you were able to write them down in the notebook. And if you ever need to pause or go back and see anything else, look at, it's like, what does it mean to simplify? What is a integer? What do those things mean? Feel free anytime. But now what I'd like you to do is take a look at these problems, and all of those skills that you just learned or maybe reviewed are going to be useful in solving these problems. So here they want you to simplify some fractions. So you're going to have to factor some of these things and see if you can cancel anything out. Sometimes they want you to note domain restrictions. It's always a good idea to do for any problem. And down here, a couple that are a little bit more fun. So these are a little bit harder problems. Notice on the top of number 5, you've got a sum of cubes. Ooh, might have to do that. I'm actually going to do these problems in another video, but I want you guys to try them on your own. If you need to check your work, feel free to take a look at my video. And good luck with that. And then there's a couple of worksheets for you to try. So if you don't want to watch any more videos today, totally okay. You can do these problems, try the worksheets. But if you need to see any of these problems, you can watch that video. Or you want to see some examples from the worksheets, you can check those out too. But everything is linked on Toddle. Give it a try. Whatever you don't finish is for homework. Love you guys. Have a good one.